Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu, and in this episode, I have the great pleasure to interview Jimmy Koppel. He is a PhD at MIT and founder of the Mirdin Company, where he teaches engineers to write better code. Join us in this amazing discussion about how to make better code and how the knowledge of computer science theory and programming languages can help engineers to achieve that. So without further ado, let's get into it! So, I've seen that you've spent a lot of time thinking about what makes code good code and how can we achieve that in the wild. What are your thoughts? What makes code to be good code and in general?
Sure. So that's very broad questions. It's kind of like saying how do chemicals work? Well, there's an entire field to that. But I have to try to say something succinct. You can start by saying, so what are the external qualities you want your code to have? You want it to work. That's first. You want it to satisfy all the requirements, including functional requirements and non-functional requirements like being performant. Then the intrinsic qualities of your product, which are extrinsic qualities of the code. So you want it to be understandable. Understandable to whom? To yourself and the people who need to read it. We want it to be changeable. Changeable for what? For the thing where it is conceivable that you might need to change. The features that you can't be 1,000% sure you won't need. And it needs to be robust. It should not have bugs. It should be easy to see there are no bugs. And when you change it, it should be hard to accidentally create bugs. And so then there are the intrinsic qualities, the facts that get it there, and that's the main thing. Yeah. So what are the things that make it more changeable? Well, so it needs to not spread assumptions everywhere. What's an assumption? That's its own topic. It needs to not have a huge amount of places where a single design decision is reflected in many parts of the code. We call it hidden coupling. It needs to be open in many things. Openness means that you can conceptually add things to some sets, like I support 10 of these kind of things, I want to support 11, and very few parts of the code should have to change for that. So ideally, just the place where you're defining those 11 things. Then robustness. How do you get robustness? You can get robustness when you have APIs that are hard to misuse. That's most ways of using them that compile are sensible, and that when you're using the wrong way, it's very obvious. There are a bunch of other things. How do you get code to be understandable? It's also a lot of things. It means, it's very easy to see what the intention of code is, and that's you don't have code that works by coincidence, where this thing works, but only if you read through 10 functions and several libraries, and you find this one thing you're worried about happening that could mess it up actually can never happen. It means that that the names are good, that from the name you can easily and correctly infer what that thing is meant to do. And so there's a lot of these for each of those qualities that I mentioned.
You've trained quite a few people to write better code. What do you see are the most common hard pieces of code quality to get right? What are the things that are kind of more common to be a bad smell and to be doing things that could be better done in different ways?
So I'll answer a slightly different question, which is about the big barrier between a junior and senior engineer. And if I had to pick one thing that's most likely to be the barrier, it's not grokking the implementation interface distinction. That's the junior engineer kind of sees the code as it is, as code, and they put down a lot of stuff, and if it works, then it works. And actually, I kind of remember being like this in my early years. Okay, so one of the dumb class examples is when you write to the stream 1 instead of standard out, because 1 means standard out, or is it 0? Well, I don't really remember now, but I definitely did back then. So let's say just 1 means standard out for sake of example. And that would not bother me at all because, like, oh, well, surely anyone who's reading this would be like educated, know that one means standard down, and get that immediately. Now, if you see that as a piece of knowledge, it's like separate from what's right in front of you. You're like, no, I want to draw as little knowledge as possible. And similar things like, if there's some fine grained facts about how the structure of your data looks, that's obvious to you as a person who wrote the whole damn system, then it doesn't bother you at all if you write code that uses very pervasive, subtle facts about how the data tends to look. And it's like, sure, I just reach 5 layers in this data structure, and I know this thing will have to be formatted this way. And well, at some point, you have something that starts to bother you, and it becomes strongest when you can very aggressively say, like, a piece of code and say, I'm going to assume, like, even though I wrote all this other stuff, I'm going to assume that, like, that all is going to go crazy at some point and get mutilated in all kinds of ways, and, like, only some basic facts remain guaranteed to be true. And I'm only going to assume those things when I write this code. And that's the implementation interface distinction.
That does sound very hard to get right. Because yeah, once you're coding, once you're into the weeds, you just start, thinking that all of these are trivial. I don't have to care about any of that. And it seems to me that this is where it's very important for you to sit back and really plan what you're doing. And I think that's where people like you come in, and you can have a good look from the outside and see the issues of the code. So how does your coach sessions work?
Yeah, so only a small minority of my work these days is in the one-on-one or small group coaching, since I've taught this course for 5 years that several other people have gone through. So nowadays when I coach, it's the people who want something they can't get elsewhere, including from my own course. So let's say when I first started, I definitely call myself a coach and not a tutor. I was inspired by a life coach I'd worked with. I got trained and certified as a life coach, and there's a lot of thinking in my feeds, and also sometimes diving into emotional issues or interpersonal communication issues that I trained the life coaching stuff to help people with. But now it's like only a fraction of my work is on the interpersonal or communication side. Most is technical, and as I've gotten more crisper and crisper explanations of how to write good code, it has kind of turned more to classic tutoring, where it's like I have these structured concepts, huge pool of them, and I'm trying to convey them to the students. So if you picture a really good tutoring session, and I hope it's really good, I'd certainly get people coming back and paying me a lot for it, then it's like that. But so what are some more distinctive things about being tutored in software design versus being tutored in chemistry? So one thing is the ability to draw on a student's own work. Sometimes have them bring them problems at work, usually with like simplified idealized code, or once in a blue moon they get permission to bring in the actual code, and we'll work with that. Oftentimes when I start with a student, I'll have them do some kind of coding challenge design exercise. They'll spend a few hours in it, so I'm going to quickly get a large list of topics that they can improve on just from looking at their code. And a really neat thing that I can do is the design exercise format, where I have someone design a program, not implement, but design a program in front of me, and I'm able to give them live feedback and often make feature requests or request changes to it that are antagonistically chosen to be hard to do because of some design mistake they made. And that's the kind of feedback that might take years to get in the wild. You can get it in minutes in one of my
I would
sessions.
like to ask. So you've been you've been pretty much part of both worlds, academia and industry, right? And it seems to me that you try to bring as much as possible your academia knowledge to industry folks. In your point of view, what are the ideas that you learn in academia that you believe that can really help industry people?
Well, so a first thing, it's kind of more superficial, but actually quite significant, is to not be afraid of reading papers in primary sources. So I do assign a number of papers, especially like classic things like software engineering works from the 70s in my course. And like, yeah, they're probably a lot easier to read than like the average PLDI paper from this year. But still, I've had a lot of people tell me like, "Wow, that was like the first time reading an actual academic paper," and I always thought it was like not it's not something I could do. It's just out of my reality, and bam, now I can do it. So this one I actually haven't really intervened on. I don't think I have not really talked about with students. I don't more people about it. But one thing I definitely wish a lot more industry was to do is so one definition I've seen of a scholarly work that's different from research work. Like you can be a scholar without being a researcher. Is work that's is put into context and cites all the other things that have done before. And that is something that industry people are extremely bad at. In fact, they often try to do the opposite, where like you go into an open source project and I'm gonna make something up on the spot. Like say it's some kind of streaming library, and they're gonna make up their own terms for everything. So like maybe they'll call different kinds of streams like rivers and creeks, and that might correspond to like a certain kind of stream that is either a simple description or maybe it already has a name. But now I need to learn what a river and creek is, just this one library, and do this all over the place. And it makes it much harder to understand a new framework and much harder to compare
But I
them.
think I think kind of like in a I can see why that may happen. Maybe I'm wrong, but like in academia, you have a very strong need to communicate your research, right? So you need to put it in terms of what people have done before. Where in industry, you really try to sell your thing, like get people hyped, and as much as the more you can get, like these flashy names and cool things, more people will be hyped. Maybe I don't know. That's what I but I agree with you. That's kind of bad.
Yeah, it's like so. I don't feel really prepared to talk about how much it actually works or it benefits. But for me as the audience, like I want to be able to quickly evaluate and compare frameworks and choosing between them. And if you use the actual language for it, I can very quickly get an idea of whether this thing is going to solve your problem. This is like and I think that does generalize. Like maybe like what's certainly different. Someone who's like an expert in a lot of things and like they've seen it's every kind of streaming library before, but I don't know. You can get a lot better if you just don't assume that this is the first streaming library your audience has ever seen.
Yeah, I definitely agree. What about some more technical things in the programming languages research in general?
Uh, think about some of the big features or things to produce in academia and academic languages. They're still not incorporated into languages. So it's a really nice thing is that it took 30, 40 years, but we now have major languages that have algebraic data types. Like it's like Rust and Swift and Scala have them in some form or another. TypeScript almost has them. You can encode, but you can code. It's like TypeScript has unions, which are different from sums. It's like most of my career, it's like you could forget about unions, and now suddenly you have to warn people about unions. They're not the same as sums, but you can encode sums to TypeScript pretty straightforwardly. For the listener who doesn't know, like you know, a, an int summed with an int is different from an int because you know whether it's the left thing or the right thing. But its union is int; it's the same as an int. Mm. I think the big thing missing from most languages is proper support for existential types and true modules. So the ML style modules or true module theoretic modules are still something that's unique to the ML family of languages. And only some of them, like F sharp, doesn't have them. I think Elm doesn't have them, but OCaml and SML do. But I think it's a very important concept that we often emulate by a gentleman's agreement in all their languages. So there's a couple aspects to this. So one is the ability to change implementation of another components that you rely on. Actually, in one of my Haskell projects, I have a thing where we can switch between the single-threaded and multi-threaded version of a memoization library. And to do that, basically need if-defs. Probably could do it with type classes, but it's like actually I think there might be performance overhead if I do it that way. It's like in an ML language, it could be so easy. And Haskell does have like a very weak support for modules, but like they did all this work to put modules in Haskell, and they messed it up by putting the build system instead of the language. So you can only do it like across package boundaries, not across module boundaries. The other thing, which I think it's going to be harder to put into languages that don't have any kind of theorem proving support, is to decide exactly what information is hidden within a module. So, example that I use a lot is sanitized strings, like which modules are allowed to know that for a string to be sanitized means that it has all quotes escaped, and it's basically a gentleman's agreement. Like, in some parts of code base, you're allowed to like index in the string directly and do these things, and other parts you're not. But that's something that's, I think we could see a lot better support for that kind of thing. Maybe not like full control over what facts are usable in what parts of the code base, but like some finer grain control about like these operations are permissible in this parts, not others, and like much finer grained than the everything's public everywhere to everyone or private to everyone kind of access control that we have today.
Mm-hmm. I don't want to put you on the spot in this question. It's okay if you haven't thought too much about this, but how does these things compare in an OO language, say like Java?
Oh, not thought about it. No, I know a lot about this. So, and a lot of these answers are going to be found. It's a paper by my undergrad advisor, Jonathan Aldrich, called The Power of Interoperability Why Objects Are Inevitable. And it does a great explanation of comparing functors, that is, modules that can depend on variant other modules with objects. So, one topic I like a lot is object encodings, which is how do you take the idea of an object and turn it into the basic type theory constructs of existential and recursive types and products. And I think it's really illuminating when you do that. And then you can see exactly, then you can start to imagine like all the variants of object systems, and you can see exactly how it compares to modules. And you can see the ways that objects are kind of more flexible, most of the time too flexible for their own good, and the ways which they're restricted. So I can go over both of them. So restricted, probably the biggest thing is that an object is tied to a value. Like you have a virtual function table and is tied to a value. And this is distinct from, say, type classes, which are very close to objects, except that the virtual function table will travel separately. So you can write a function of type A to A to A with a type class, but you can't probably do that with an object. Okay, we can. You can use something more complicated called f-bounded polymorphs. If you want to write a number class where you get a float as a number can be added to a float, and an int as a number can be added to an int, but you can't add them to each other. Or I guess more realistically, like you would want to do that for like an int versus a matrix. You can do that with f-bounded polymorphism, but I'm not even sure that's okay. No, I take that back. Yay. Okay, so the binary function thing is a solved problem. What's not a solved, what you can't do with objects though, is that the constructors have to be separate, and that's basically the reason that factories exist. Is that, so I'm going back to my example earlier of the concurrent versus single-threaded memoization. It's like if you did that with objects, you need to have separate code that calls the single-threaded memoization table constructor, or in separate code that calls the multi-threaded one. And then from there, everything else could use an object, which is one or the other, you don't know which. But the code constructing them has to be separate. And then, or it can create a separate object, which is a factory. Then you still need a place that chooses the factory. And then it's actually kind of difficult if you want to tie the factory and the implementation together. It's like, say, this thing's a factory for this kind of thing, this is a factory for that kind of thing. Objects don't make that easy. So that's the constructor issue. And then there's the restriction issue, which is, there's a great line from the paper, one of my favorites of all time, on Data Abstraction Revisited. Let me check that title. On Understanding Data Abstraction Revisited by the late William Cook, who is your grant advisor, I believe. It's a great line that is, objects let you override arbitrary code paths. They're designed to be as flexible as possible. it's almost like they're designed to be as difficult to verify as possible. Like an object is meant to be like a single thing that deals with everything else by their interfaces. And that's what you want in a plugin system. That's what you want in like an extensible GUI system and things like that. But it's not what you want for most things. And so you're getting all this extra flexibility, which is actually a bad thing if you're using objects to get your to what's called dynamic architecture, meaning that it's not exactly determined which component connects to which other
It's
component.
I think it's interesting how, in the I want to say in the 90s there was a huge hype over object oriented languages. Even like I think Uppsala was more or less created more around that time, and it was a big conference. And nowadays, even Uppsala is slowly shifting towards more other kinds of verification and object oriented languages. Research in particular is losing a lot of traction, and there's a lot of discussion on the trade-offs between all of that. So yeah, there's a that would be a whole topic on its own. But talking about like this shift towards a more formal methods, or yeah, the shift in interest in formal methods and type systems and even verification in general, right? How do you think this all of this can be used by the average software engineering? What are the tools do you think are worth, or that we're going to see more in the software engineering industry in the future?
Yeah. So, I would have been more prepared to answer that a few months ago, given that with the rapid progress of AI, say the future of what software engineering will look like, I think is kind of uncertain right now.
True. That's very true.
So, it's, it's things like, maybe it's like maybe you can't get an AI to write flexible, easy to evolve code, but if you can get it to write a lot of code, then making the code easy to change kind of seems less important.
Well, let's pretend we're recording this before AI, these kinds of AIs
Oh yes,
existed.
yeah. So let's go to yesterday's future. That's
Yeah.
so for yesterday's future. So I think the trend of fancy, more expressive types becoming more and more mainstream is going to continue. So like I do see this with, well, so first, um, the idea of dynamic typing is very out of fashion, where increasing fraction of Python is now typed. Uh, JavaScript's giving way to TypeScript, and TypeScript has, in some ways, the fanciest type system of any major language. It's more fancier in a lot of ways than Haskell. Actually, my business partner Nils has a blog post where he created tic tac toe in the TypeScript type system. That is like you you instantiate a type, you pass some subtype parameters corresponding to tic tac toe moves, and then you mouse over some things, and the type inference tells you the current state of the board. Then that's obviously just a demonstration of how extreme you can get, but I think like more precise and flow sensitive types are going to become more common, both as more languages offer support for them and more people learn how to use them. I don't see them becoming dominant soon, but I think sophisticated static checkers and model checkers are going to become more common. So actually, I kind of saw this recently when Dejin Park, who's a PhD student at Illinois, now works for Andreessen Horowitz in their crypto arm, released a symbolic execution engine for Solidity for blockchain, and like just watch the reception he gets. It's like, 10 years ago released this sort of thing, and it'll be on a big outcry about how formal methods are overkill or silly or like not solving the real problems. But no, it's like everyone's like, yeah, this is great. More of this. It used to be you talk about static analysis online, everyone assumes you mean the linter. And And it used to be that like no one in industry knew what Z3 was or SMT solving, and now you like read. It's like I've been on Hacker News since it came out like 15 years ago, and it's been a shift.
Those things are really exciting. Do you know um, what kind of formal methods more specifically they use for the blockchain technology?
So I know some of what's available, but I don't know their penetration. So Tora and Veridice are two major players in this space. It's actually it's kind of a joke right now. It seems that like large fraction of PL professors are founding blockchain verification companies. So you have Ishil Dillig at UT Austin with Veridice. Uh, you have Grigori Roshu at Illinois with runtime verification. You have Jung Shan at Yale with Certic. Like although they're mostly a they're mostly a shop where they have several hundred people in China doing manual audits, but they also do some verification. And and then you have Muli Sagiv in Israel with Satora, which has like 40 million raised and 70 people. So I can't speak as to how much of the market they have, but I do know that Satora's websites brags about how their customers have several $billion of assets under
How do you see
management.
this? Do you think that's a good thing for formal methods research in general, or do you think that, I don't know, maybe it's becoming a little too going towards the wrong course?
Well, for contrast, there are also hacks in traditional finance, like the Swift protocol seems to get hacked a lot. That's why aren't they using this stuff? So like all these kinds of programs are very high stakes applications, very attractive for hackers that could benefit from this kind of technology, and and it's great that the blockchain world has, at least in the short term, been making formal methods cool and pumping a bunch of money into it. It's like it's not a very diversified customer base if they're the only ones pumping money into formal methods, but it is a customer base, and that's great.
Right. I like that. I hadn't thought on those terms particularly, because yes, there are many other kinds of assurance that you can get for driving your software towards as correct as possible. And I might be wrong, but I don't think formal methods, our research in formal methods is there yet. We're kind of like young applying this technology, right? That's that's a good point, I guess.
Yeah, and it kind of sucks to say that given the community has been around for several decades. I think CAV was started in the 80s. That's
Oh, technically, all of this started with church, which started computer science itself.
ha. Yeah, it depends how broad you want to cash in
Yeah.
at. It's
So going, so circling back to this notion that you said that types, like dynamic languages are growing out of fashion. Do you think then that type systems definitely helps to write better code and prevent errors?
in the right hands, absolutely. Like they're, it's kind of tautological. It's like saying do railings help people falling off stairs? Yes, and there's like you can do experiments where you try to have someone run towards the edge of stairs without a railing. It might hurt in both cases, but where they fall off is different.
I like that analogy. It's a pretty good analogy. Well, you also have this well, you have many articles on our website that I definitely recommend the listener to take a look at. There are some pretty cool stuff there. In one of them, you go through a few branches of what do you call theory? Well, yeah, theory, computer science theory. There are a couple of branches in theory that you give some thoughts on why or why not programmers should learn about them. In particular, you mentioned there type theory, program analysis, program synthesis, formal verification, category theory. Could we go through these and have some
Sure.
thoughts on why you think they might be useful or not?
Yeah, absolutely. So this is my blog post, why programmers should, int, in parentheses, learn theory. And it's about kind of what I call software engineering theory. It's like this parts form methods in PL that are think relevant to software engineering, as distinct from what just goes in label computer science theory, where you talk about randomized algorithms and computability and complexity and that's these statistical power of different learning algorithms. This is the kind of theory I think is applicable to all kinds of software
So,
engineering.
what are the ones that you think are the most useful and why?
So the five areas that I identified were type theory verification, category theory, program
And
analysis,
synthesis.
and synthesis. Yes, and without a doubt, of all those, said type theory. And the reason is that type theory it structures how you write programs and how you can write programs. If your language is dynamic, then you can still impose a type system onto the language that describes the structure of constraints that is already there, that you're already following as you write your code. And understanding that is very
Don't you
powerful.
think that that's a little too hard to learn like that, or do you think it's a time well spent?
Like, do I think that what is too hard? Do I think that it's too hard to understand what a product is, and that both tuples and structures are products and they're interchangeable? No, I don't think that's too hard. Do I think it's too hard to understand the lambda mu calculus and how to do cut elimination in the presence of continuations? I don't know if it's too hard, but I think most people won't care enough to do it,
Yeah.
even though it has some super cool results. Do I think it's too hard to let's see, do I think it's too hard to understand John Reynolds' abstraction theorem and how to perform theorems for free? Well, it took me about 3 attempts before I succeeded in understanding it, and I only still understood the Philip Wadlow version and not the original John Reynolds, which still haven't attempted. So yes, I do think that's too hard.
That makes me feel better because I'm still trying to understand that. I'm almost there. I feel.
So you also asked, sent an email. Tell us a practical example of how theory has helped your clients. So, so I certainly have my own speculation. I can talk about how it's helped me, how I think it's helped people. But I did ask this to a few people and got a couple answers. So it's one of my students told me last night when I asked him this. He still doesn't know much theory, but he said, well, there's a general thing about learning any theory that helps structure your thoughts, helps you understand the subject better. But he actually brought up that long before he met me, he learned loop invariance in college as a sophomore. And he said, like, it gave him this power to understand loops and how to debug code with loops that some of his friends didn't have. Like, he had a friend, like, with a pretty complicated function that had a loop, and he was, like, clearly not understanding how it's supposed to be done. And he told his friends, like, think about the loop invariant and taught him that. Another answer I got, some people have talked about using a shorthand version of pre and post conditions like you see in Hoare logic. So, like, I teach people about hidden coupling. It's like when things change because they have some shared design decision, but they don't actually reference each other. But often when you write down the pre and post conditions of the code, then their coupling becomes more clear. So one of my students said that he's been using that in pull requests to show with this hidden coupling. But more generally, he also says that it's like he has this for foundation that he can set off and learn. So I mentioned earlier how true modules and like talking about what facts may be accessed by different parts of code. It's a very important idea a lot of people understand. But really, that's powered by existential types. So the same student says, like, he still doesn't fully understand existential types, but like I've given him the foundation for him to continue exploring on his own. Teach a fish, to teach a person to fish. Don't teach a fish. Something I can say is that for my equality constrained tree automata paper, this new kind of solver I have is very good at certain kinds of synthesis problems. There was a piece of it where I hired a contractor to help with it. The contractor is Edsko de Vries. He did such a good job that he became a co-author because he contributed a core piece that makes our thing much more general. But even for his normal code, he was brought in to do performance optimization first and foremost. And and as he's doing this, it's very clear that someone without this kind of background could not have done the work he did. It's so we have this complicated data structure, and he's switching it to this other form, and he needs to show that's going to be equivalent to the original form and not mix things up, while also being more performance. And he actually put proofs in the
Oh wow.
comments, equational reasoning proofs showing that this thing worked properly. Yeah. I think it would have been hard to write this code without that. And I think that's just outside the abilities of most programmers. But this is not just learning a bit of theory. He actually has a
Right.
PhD.
But it's pretty cool. It's a pretty cool application of this knowledge in the industry. Yeah, I like that. I like that. Type theory definitely can give you a lot of. That's usually how I describe my research to other other areas of computer science. What do you do? Well, I study programs in general and how can we reason about them in general. What can we abstract away all of this noise of different syntax, of these discussions of should we be using brackets or tabs or one or two spaces. That's useless. That's not interesting. What's the essence behind the programming language? And I think that's what you achieve in type theory, and that's what we try to study. And so I definitely agree with you that it can be very, very useful for the average programmer to learn. I'm just sometimes I feel that I don't know, maybe you have to go a little bit too deep to really get the feeling of why this is interesting, why you should care about this, right? But I definitely think that people should try at least.
Yeah, and I don't think I don't think that's the case. I think the basic type theory are rather
Right.
simple, uh, and I think it could be taught to a lot of high schoolers, even with the formal rules. And I think it pays some dividends pretty quickly. Now, in contrast, in the same blog post, I talk about Cox style verification, which is basically the more advanced dependent type theory. And I think there's also a lot of value from being able to explicitly prove theorems of products of your program and see them as distinct from the program itself. It goes back to what I was talking earlier about the implementation interface distinction. And I think to fully understand that, it's really hard without having done some work in Coq or a similar tool. But to get there, you're also going to have to learn a lot about tactics and type versus prop and a lot of other things that is a ton of burden before you get to the bits that philosophically carry over to everyday engineering. And so for that, I don't think the trade-off is worth it. And I think it could be. And I still haven't really learned lean. Maybe you can get to there faster with lean. You can write a new tool that's just the intuition for software engineering relevant parts. But my exposure to verification is it's I have a few hundred hours in Coq, and I'm still feel like a noob.
Yeah, for sure. Do you think there are any of these tools for, maybe some sort of formal verification, even synthesis that it's worth checking out, like the average programmer to try and learn and study a little more,
Huh.
or maybe even using in their
Um.
project?
Well, I said earlier that people should understand ML module systems, so that implies learning SML or CAML. Turns actual checkers verification tools. Z3, I think, is a lot of bang for the buck. It's useful in a lot of things. That's also kind of like saying that someone should learn how to use any other kind of solver. Yeah, there's a decent chance that okay. So when I had an internship at a hedge fund in 2011, the very last thing I used an actual linear programming solver because there was something where they had a brute force optimizer and it's replaced it with this linear programming engine. And it's great they knew how to do that, but that's not particularly deep. And I think most users of Z3 would be the same way. So even though it's like a tool that came out of kind of PL and automated theorem proving stuff, its uses would just be like random stuff everywhere. But once you learn a Z3, it's only a small extra step to learn about how to encode a program into Z3. And so even if you don't actually wind up using that, I think being able to do that is still very cool. And so, like in my strange loop talk, where that's this section where I try to teach that conditionals are a logical notion and not a syntactic one. And I show that's like pretty much determines what the conditional is. If you create a Z3 formula encoding the relevant part of your program, if you don't have a way to encode it, that's not a logical formula. That's not a conditional. Then you haven't limited a conditional.
My biggest issue with say Z3 is I agree it's not too hard to use, but it's extremely hard to debug.
uh, yeah, actually, I can't say I've run into that before. Okay, well, actually, we'll say if you have a verification condition generator and you have a 20-line program that you're generating a 100-line formula for, then that is not all a good way to debug what goes wrong.
Yeah. So you've done some work with program synthesis in your PhD. How do you see that field in the sense of going forward towards the future? How do you see it maturing and being used in general? And what are your thoughts about program synthesis?
Uh, so I actually don't feel very up to date in the field right now. As well, so one thing is that it's turned into an AI field.
Right.
There are now more synthesis papers published in AI conferences. It's been a case for several years, and more synthesis papers published in AI conferences than in PL conferences. And it's not quite a fair comparison because it's like the PL papers are usually bigger, quite literally. It's like often 3 times many pages. Uh, but I think it's probably true even without that. And then we get to the old gripes about they're not citing. We were here first. We did all the cool stuff. They're not citing us. And anyway, I mostly don't read the AI papers yet, so I'm not really equipped to speak about what's going on there. On the PL side, I'm also kind of out of touch. Like also particularly like I'm a year and a half out of grad school. I read, I don't read no papers, but much less than I used to. And even still, like synthesis is never my core area. It's always what I call meta programming.
What is that?
Which meta programming is making tools easier to build and more general. And it is a less charitable thing is that it's a pretentious way to say software language engineering, which is an established field. But it's basically, I think the things going to that label tend not to be like language workbenches and to not be cool enough. So I did meta programming for the stuff that involves some very fancy implementations and some search and solvers in order to generate tools to make tools very general. So core example of this is my mandate paper, automatically deriving control flow generators from operational semantics. So control flow graph is a graph saying the order that stuff happens in a program or could happen, all possible paths in this control flow graph. So every compiler will have a control flow graph generator, which takes a program, gives you a control flow graph for it. And I built the world's first control flow graph generator, which takes in the operational semantics of a programming language and generates a control flow graph generator for that language.
Wow.
And that is meta.
That is super cool, actually. And how do you write down the operational semantics for a language in that tool?
Very carefully. So it uses structural operational semantics, like Gordon Plotkin 70s standard thing. We have, it's a data type. So we have a data type for writing these down, and that creates an embedded DSL for it. So it's pretty standard stuff. The main twist is that in this tool, SOS actually stands for not for structural operational semantics, but straight into operational semantics, where I've taken the normal inference rule notation and I've basically replaced it with nested let bindings.
Oh,
And this gives an ordering and a structure to the rules that makes them easier to work with.
gotcha. That's very interesting. And then you can generate the so yeah, you generate a control flow graph generator for this language. And I remember seeing something about generating things for many different languages. So what languages can you apply this to? Any language at all?
So there are some restrictions in the form of the rules. Some of that's kind of innate to the approach. So actually, this might surprise people that many languages don't have control flow graphs. In fact, there is no such thing as control flow graph for C.
Really?
Yes, and the reason is that evaluation order is unspecified. So if you have a big nested expression, like a plus b plus c plus d plus e, and like lots of parentheses all over the place, you can jump back and forth arbitrarily, evaluating this parts in different order. It actually has a concurrent semantics. And with that, there is no such thing as the current program point. In fact, even if C didn't have threads, you could actually encode threads into its arithmetic, just because it's allowed to jump back and forth. Now, it might actually compile with interleads fashion, but the semantics allow it to do so.
That's crazy.
So yeah, so because of that, C within expressions. So at the statement level, it does have a current control point. Actually, so yes, I guess I lied. In mandates, there's an option. You can configure it to skip over all expressions. That is, say all expressions abstract to just there can be some value, and with that, then all the non-termism will get eliminated. But if you do include the expression level, there's no such thing as a current control flow point. So instead, you need a Petri net called a sea of nodes representation to properly model the control flow. Anyway, so that's one limitation mandate, which is more intrinsic, that you have this kind of non-determinism. Then there's no current control point, and so this really properly is no such thing as control flow graph for that language. There are some more arbitrary restrictions, such as so. Basically, I was kind of lazy when implementing the rewriting engine. So mandate's heavily steeped in term rewriting theory, and like the proper tools like MAUDE can deal with like lists inside of maps, inside of trees, inside of maps, and so on. But my tool can't. And if your program state is very complicated, as it will be for any real language, then you'll have that kind of
Rewrite
thing.
theory is actually a very interesting branch of PL, I think, because a lot I was surprised one time that I put my hands in a rewrite theory book, and a lot of the problems that I was trying to solve was already there, like in the first few pages. Well, so yeah, it's a cool branch. But so in our private communications, you mentioned that there were a paper that you submitted like many times. Was it related to this tool?
Yes. This is the paper that took 9 submissions to
Nine
get in.
submissions. Wow, that's insane. And you were still in grad school when you were doing that.
That's right. Actually, so it was not accepted until after I graduated, actually. And so one of the very important piece of advice that I got from Martin Reinhard at MIT is he says, like, to get papers in, just roll the dice more.
Wow.
If you think your paper is good enough that it doesn't need revision, then just try to minimize the effort to resubmit and just resubmit more and wait. And so I followed that advice. So I stopped submitting to PLDI because PLDI had a different format and a much shorter page limit. And so it would have been a lot of work to like switch submission to be in PLDI length and switch it back if it got rejected. So I just did my submissions to ICFP and Koppel each year for several years. And something interesting happened. Submission number 8 was to Koppel 2022. And its scores were actually, I think among the worst of any of these submissions. So in the second to last submission, it got BCC. That's 2 week rejects, 1 week accepts. I'm not sure I changed a single word when I resubmitted to ICFP that year, but it got, they were on a 1 to 5 scale, so it got 445, like accepts, strong accepts, and then after rebuttal was changed to 555,
Well,
strong accept, strong accept.
jeez.
They were basically the same submission, but it was just roll the dice again with who was reviewing it.
Wow.
And that's not to say the superiority of ICFP over
Right.
Koppel, because I have had other ICFP submissions in previous years where I got low quality reviews. Actually, like I remember one submission where this guy. So part of the process of turning a semantics into orthograph is it turns the semantics into an abstract machine first. And there's this guy Danby that's kind of been his thing in his space. He's done a lot of work in that area, and so I've read a bunch of his papers and I cited a bunch of them. But then, this one reviewer at ICP, this is 2020, 2019, 2020, I think, said, well, there's this one Danby paper, one of the ones I hadn't read, and doesn't he do that part of the paper already? How is it different? And so I read, during the rebuttal period, I read that paper, and I wrote a long description explaining like how it's totally different and doesn't come anywhere close to what we do. And I'm pretty sure the reviewer did not read my rebuttal at all. Not that part. It's like, oh, well, clearly you need a lot more to explain it. Yeah. So, yeah, actually, this must have been ICP 2019, because it was later in 2019 that I actually met Danby in Singapore. And so I was actually able to include a sentence in the paper saying what he thinks of it. And to preempt criticism of, well, didn't he
Those
do this
are
already?
really, really hard. I mean, I don't know, man. I feel that academia right now is in a really weird spot because there's just so many people going to grad school that wasn't doesn't seem like it was like this before, and we have this huge problem of scaling for publishing and how and what can we do about those things. So like are problems that are kind of open for us to solve, and what I mean by us is like us, next generation of researchers. I think that's my view. But it seems to me that you are kind of slowly migrating out of academia. Is that the case, or do you plan to do something? Uh,
I mean, I'm mostly out. Like, I went through grad school as a grad student with a foot in the startup worlds, and now I'm, well, kind of the startup world, but generally in the software world, the industry software world, but still a foot in academia. It's kind of flipped. Uh, and like, I'm basically out, but I still attend my old lab meetings. That's I am. I still like to visit universities and give talks when I travel. It's like, it's like the, it might take several years before that talk really starts getting stale and people know it already. It's like, so next month I'm going to the Ilko Visser Commander Symposium for a professor who's, I mentioned like my meta programming, I just kind of see as like the cool parts or the cooler stuff and the same goals as software language engineering. So one of the giant software language engineering, Elko Visser, just had a stroke and suddenly was found dead on the sidewalk about 1 year
oh,
ago.
I'm sorry.
So I'm going to his memorial where people will give talks about him and about things he would have been interested in. So I have a small paper there. It's like something I did years ago but never wrote up. And then afterwards, I'll be visiting a bunch of other universities in Europe and speaking about my work there. So like I still do that kind of thing. I still have a few collaborators where I do a small amount of work, but mostly supervise them. So actually, we got a paper into ICST, International Conference on Software Testing, where the last big thing I did in grad school, it's basically a new kind of solver that's really good at a bunch of problems. So we used it to generate test properties for property-based tests, and got that paper in. So like 90% of the work was done by my collaborator Matthias, but I still say, well, it's a last author paper for me, and there's and like there's one other project I'm on that's also about related topics. The solver is based in tree automata. There's another tree automata paper I'm on, actually two of them. So I still have a few collaborations like that where I'm kind of taking advisory
That's
role.
nice. That's pretty good. I feel. I mean, I feel like there's so much pressure. Like once you're inside academia, there is so much pressure for you to publish that I don't feel that it's necessarily you're necessarily doing like impactful work that you could if you had more time or more leisure. Because you're so pressured to do those stuff. So I think that maybe people like you can have even more impact actually in academia because of that.
Well, so that does connect to my thoughts. Like one thought is that Linux has done more for the state of software engineering art than a full decade's worth of ICSE papers. So there's the direct impact of software engineering and that sort of thing. Another thing is the amount of boilerplate container that needs to go with a small kernel of an idea. So if you have an insight, you can build a new thing that's successful at that. You've done only a fraction, the most important part of the work to get a paper, but only a fraction of it. Because you still need to write the paper, write it very thoroughly. Actually, I mean, that part's probably good. You also need to do experiments, even it should be obvious to someone who understands it that your thing works well. You still need to defeat the laziest, most critical uh, reviewer. You need to compare it to everything. So you need related work, which it's something I always took very seriously. One of my papers has cites about 90 other papers because it's about semantic code search. It's kind of a broad term. It's been done a lot. And so I had to skim through about 70 other semantic code search papers to compare mine.
Wow.
Uh, yeah, that's oh yeah, actually, I got very, very fast at that. Like set a 7.5 minute timer. My goal in that 7.5 minutes is to read enough the intro and the overview section that could write a paragraph about what it does. Just do that over and over. Even if I need to set a second 7.5 minute timer, I'm still one.
Wow.
Yeah, let's say doing research with a very effective printer. We can print out stacks of these papers. It's a very good thing. So go to university that does not skip on printers.
That's good. Most of my reading is actually done in my virtually in an iPad or something like that. But I feel
Yeah.
it's just so much better to actually have the paper on your hands.
Uh, uh, anyway, yeah. So this case in point of this is the field of linguistic anti-patterns. So there's a professor, I think Arne Dova, I think's the name, who decided to study this thing called linguistic anti-patterns of like certain structured ways of bad names. And so what? All right. So say you went to do this, you would find certain structured bad names. What do you need to do? Well, you need to talk about other kind of anti-patterns and compare it, which sounds like not an easy writing task because it's different. You need to define your anti-patterns, and you need to be able to say their prevalence. So that means that you need to either be reading a lot of code very carefully, a lot of understanding, or make them simple enough and then write a scanner for it and still review a lot of code to find instances. And you want to talk about like what fraction of code base is going to have these anti-patterns. You want to talk maybe want to run a study about how it affects people. And there's a lot of things that go into creating a publication, and they're differing value. It's like the core idea is most important, then the implementation. But a lot of the experiments like are the same amount of some experiments are very valuable. They really could prove it works. Some of them are really not valuable. Like they don't really add information about how good your thing is compared to the state of the art, but they do defeat lazy reviewers who think like a big thing I learned is that like there's a it's kind of knee jerk reaction for viewers where like you say certain words, they'll bring you certain criticism.
Right.
Like you say the word correctness the wrong way, someone's gonna ask you to verify it in Cock if you're in an appeal
Yeah.
conference. Uh, it's like no, this thing's already 40 pages. It's gonna be second paper. That's um, if you mention a limitation has someone is likely to harp on that as actually being a much bigger deal than it is. So, you know, okay. So one thing in mandate, I know I mentioned earlier that when there's non-determinism, then when there's okay, not non-determinism. This is separately. So related to non-determinism is when a single separate program actually involves uh, executing two parts of the program, not just interleave, but actually simultaneously. So, it's like imagine, I don't know, I guess you could have this. A real example would be like a barrier. You say like, and at the same time, all threads are going to pass through. And you write that into just semantics. As like a single step is many things happen, not interleave, but at this literally at the same time. So if that happens, then you would get what I called an up-down rule. So the only thing you know about the up-down rule is that like they describe situations like that where multiple things happen simultaneously at different points of the program. And so this is kind of niche, and it makes sense that we cannot do it with an up-down rule. So I mentioned this, and a reviewer said, well, clearly this is bad because you need up-down rules to write language semantics. And like, A, no, you don't. B, why do you think that? This is a term I made up that only makes sense in the context of this one formalism I used here, where you have the up and down arrows, and you see the up and down arrows in the same rule. It's like, you have no idea what this means because I just made up this term. It is even a useful concept outside of the context of this paper. You have no idea what this means. How can you possibly say that? But I say it's limitation, knee-jerk reaction. Okay, so where was I before I went down that tangent?
We were talking about how being outside of academia might.
Oh yes. Sorry. So I was talking linguistic anti-patterns. But yeah, so it's talking. So that example, like the kind of why that kind of review phenomenon causes you to spend a lot of work on experiments which are actually not that much valuable. They're actually not that valuable. So the existing academic work on linguistic anti-patterns, what they did to produce something publishable, and they chose like a list about 19 hyper-specific anti-patterns of the form like this function is named get something, but it does not return a value. Hyper-specific. This function name is something, but it doesn't return a Boolean. And then, so that's the kind of things in their list of 19. And then they can write a scanner for that. They can look for examples. They can do experiments where they see how much it actually confuses people. They can check all the boxes that you need. But I like this idea, but I did not like the implementation. So I just created the website linguisticantipatterns.com, and we created our own list of anti-patterns. We did not jump through the same hoops as them. So we just gave the anti-pattern called like name type mismatch that actually covers a large fraction of the original 19. And what we do for that, we give a few examples, and people can understand that and apply it in their work. And maybe it's a lot harder to like do a study where we see how many name type mismatches are in a code base. That's hard if you don't understand the code base. But I think what we did is ultimately more useful and impactful. And that's so instead of this list of 19 that's hyper specific, we have this list of 6 that's kind of where each one's kind of broad, and we can give a few strong examples of where it's hurt people in the past and people can learn from it.
That's pretty cool. That's very nice, too. I didn't have the chance to look at that, but I saw also your blog post on the sources of power, which I liked a lot, and I wanted to bring that up because okay, so if I understand correctly, the idea. Oh, by the way, sorry, I'm changing the subject. Was there anything else you're gonna mention on that?
No, I finished that story.
Okay. Yeah, so sources of power. So if I understand correctly, you should be looking for things like to stand out in life in your career. You should be looking for things that people are not doing, but it's worth doing. So people didn't notice that it's worth doing, but you did. So you go ahead and do that, and it's probably lead you somewhere nice, somewhere well. And I feel that that's kind
Yeah,
of I really like that, because it's how I feel about this podcast, because I really wanted a type theory podcast and nobody was doing it, and I'm like, okay, just do it, whatever. And
yeah. It's going to become much easier to become known, to be known in the research world by having this podcast than by going to lots of conferences, giving a lot of talks, writing a lot of papers, publicizing your papers well, even writing blog
yeah,
posts. All those things are way more competitive than a podcast that's actually aimed uh, in significant part at researchers.
I wanted to ask you then, what are your stories about finding your sources of power?
I mean, I think my business overall, doing advanced general training for software engineers, it's like, well, like a lot of things I write about, I'm kind of the first to write about it. But it's also true that often when I explain my ideas to PL academic, they can understand it way faster than even extremely senior industry people. So, like, I don't like a lot of the insights I've had. I don't think I'm the only one who's had them. Uh, certainly, like a lot of PL professors can go on their own rants about what they think software quality should be based on their understanding, and some of them would say similar to what I say. And certainly, when I first started, it's like a lot of what I come up with is since I started teaching it. So like a lot of other people could have started on this path, but I'm the one who did. So here I'm sitting in a very comfortable space in like a market that's very valuable, very competitive. I think that itself counts. Yeah, and so when I applied for the Teal Fellowship over a decade ago, um, like motivated me was someone commented they thought it was disproportionately valuable to how competitive it was. That it was a new thing, still had a lot of stigma, but it came with $100,000 and like fame and glory and a great network. And and so I
What
applied and
fellowship
won.
is this?
This is the 20 under 20 Teal Fellowship. It's where Peter Thiel paid young people $100,000 to drop out of school, which in my case, I just
And
graduated
that's
early.
it? All you have to do is to drop out of school?
Well, yeah, it's called the Drop Out of School and Start a Company
Oh, and sorry.
Fellowship
Okay.
because that's pretty
Ah,
accurate.
okay.
Is you're expected to be like working on some great world changing project, which for most people meant a company.
Right. And you have to have a really good idea on how on what to do in this company then. Is that right? Like you need to really sell it
Yeah,
and convince people that it's gonna be good.
yeah. I mean, nowadays it is more explicitly company focused, but back then they took people who wanted to do independent research. So probably the most famous and successful person who entered the Teal Fellowship and went down the independent research route was Christopher Olah, who is a good friend in my year. And when he first joined, he wanted to write 3D printing software and to use citizen journalism. He had a friend who became infamous for taking pictures of the G20 conference in Toronto, showing how a lot of security measures were just a security theater. Some people did not like that. He got accused of terrorism and went through absolute hell for several
Wow.
years. So Chris was doing a lot of citizen journalism on that. Uh, so, but in the process of doing this and having all this time for not being in school, he joined a Neuronets reading group in late 2012. And today he's one of the most famous Neuronets researchers as a co-founder of Anthropic.
That's amazing. That's really cool. I was thinking, I also remember at this blog post about abstraction and not being what you think when you said about the
Mm.
existential types. Um, could you give us a little bit of an idea of how cumbersome maybe the idea of abstraction is in computer science, and how people talk about things that maybe they think is an abstraction but it's not, things like that.
Yeah, so abstraction is an idea where I think there's a very elegant and very crisp answer to what abstraction is. It answers all the questions and has all the intuition. And it's been around for 45 years, and yet it's still not very well known. So An abstraction An abstraction is a mapping from some more complicated domain to some simpler domain, where you're able to do some of the operations in the simpler domain and still get precise results. So the most trivial example often used in textbooks is um, that's take a real number to its floor. So you can say the number with this abstraction, this mapping, the number 4 represents all real numbers between 4.0 and 4.9999, repeating. Uh, and then when you add two of these things, like you add 4 plus itself, you get a number between 8 inclusive and 10 exclusive, and it's still pretty precise. It still carries most of the information of actually doing the addition in the reals, but it's easier. And so, but it's kind of weird to say that's like integers are abstract real numbers, because the information is actually in the relation in that mapping that I just mentioned. So you say something like a file system is an abstraction for the hard disk, that kind of irks me, because like a file is a new concept that you created that actually has its own data structure associated with it concretely. They're like separate from how a hard disk works. It's like it's its own thing. But what is true is that when you do file operations, like you read and write, create files, that could correspond to a large number of low-level actions on the disk or on a server or in memory, anything you put behind a file system. And each of the mappings between these low-level operations that that implement it, and the basic operation of here's open, read, write, and the relations and behaviors it should follow. That mapping is the
And why
abstraction.
are interfaces not abstractions? Or maybe they are. I don't know. It seems like there's a little bit of discussion in the
So
film.
so it's it can be useful shorthand if you know if you understand what I'm trying to explain right now. But it's always a grammatical type error to say that this thing is an abstraction if that thing is like something you have in your code, because the abstraction is a mapping between the abstract and the concrete domains. So you could say that there is the more about to say it like there is an abstraction between this data structure implementation and its interface.
Right.
It's like when I'm pushing onto a stack, that's an abstract operation, and it's implemented by like incrementing certain counters and moving some pointers. But if you just say, but it's kind of a misnomer to say like the stack itself is the abstraction, without saying without saying it's a what's abstraction for. But even still, like the interface, that's also like a code file. Okay, we'll see like the interface and abstract concept. We see the interface as you go into Java or TypeScript, you write interface stack open brace. It's like that's a piece of your code. It's its own thing that you can use. It's not. It exists. It's concrete. It's not out abstract in the ether.
But it seems to me then that, say, Java abstract classes are an abstraction somehow of the actual implementation, right? In a sense.
So as I said, like there take the abstract idea of an interface, the mathematical idea of an interface, as a bundle of operations with certain laws about how they're supposed to behave, and then there should be a mapping from your implementation to that, where where certain operations could correspond to a number of different concrete behaviors, but you can still make predictions about what it should do based purely on the method calls or the abstract effects. It's like, yeah, that's an abstraction. Uh, but you don't get that automatically every time you write the word abstract
Gotcha.
in Java.
Gotcha. Right. Right. I see. I like that definition of making things going from going to a simpler domain. I think it reminds me a little bit of another episode that we had about the notational semantics, like versus operational semantics, things like that. Because that's kind of, if I understand correctly, I don't know that much about the notational semantics, but I feel like that's kind of the idea, is taking something from a hard domain and then denote it in a simpler domain and work from there
Well,
in a way.
I have also not studied detailed semantics. It's a topic that's fallen out of
Yeah.
favor. But my main exposure to it comes from reading Olin Shiver's thesis, the one that invented control flow analysis as we understand it today. Uh, and so he defines his language with with a denotational semantics, and like it basically felt like an operator semantics in disguise. Like
Right.
he had his Lisp, and then he had like lists with math notation, and it works the same. And the denotational semantics is like a mapping from lists to list with math notation. And I'm like, I don't this like what do you get from this?
Yeah. Yeah, the notational semantics is, again, I don't know all that much about it, but it seems to be hard, to be hard, a hard subject, and you really have to understand what's going on. I don't know. But anyways, I, I think I've covered everything that I wanted to cover in this, and I would like to ask, how can people find you, and if they are interested in hiring you, what should they do? Things like that.
Sure. So it's yeah. So I run Mirdin, Mirdin. We are the code quality company, and we do advanced trainings for developers who want to improve in certain ways, especially ways to get a deep skill that help them all kinds of software engineering and are not tech specific. So our main product is a web course. Our next cohort starts in May 4th. You can go to Mirdin.com and check it out. And we're also in the process of launching our new self-service offering. So if I sound good, I might like to think it's because I have a nice voice, but it's probably just because I have a nice microphone. The reason is which has been hard at work recording really polished lectures for the web course, and we're also starting some work on some AI tutors to help give you really good feedback for exercises. So you have that to look forward to. You can find my blog at pathsensitive.com, PATH, pathsensitive, SENSITIVE.com. That's where I write about all kinds of software design topics and sometimes other things. I was surprised when Pedro brought up Source of Power, which is before I started writing about software design. It was my first successful blog post. I think got to number 2 in Hacker News for a while. But also with Mina.com, you should subscribe to our newsletter, Arch Engineer, where we have a lot of really good content every month. It's that it does not make it into the blog. So let's see. So when I had a recent one about applying the 5 whys to when you have a hard day of coding, things much harder than it should, to getting a lot of insights. And I'm working on one right now. It says it's taking a really good blog post by Bob Harper called Modules Matter Most, which is his take on the interface implementation boundary. But I'm basically rewriting it to be much more understandable to a wider audience who doesn't already know off the top of their head how ML modules work and how type classes are different and can read type theory notation and all that stuff that Bob Harper just likes to take for
I really
granted.
like the idea of emails. What's the name? The email newsletter. I think we should.
Arch
Right.
Engineer.
I think we should do that more. I think should have more people doing that, because I think the level of noise that we get in social media is just so high nowadays. Like, to get something interesting out of Twitter or Reddit is just have to go through so much trash.
Yeah. Well, your wish is granted because a lot of people and a lot of engineers have newsletters now. So I'm very happily subscribed to Hillel Wayne's. It's computer things. It's he's now doing it 6 times a month and is off Twitter to focus more on the
Nice.
newsletter. And it's about it's basically whatever he wants. So he writes about things such as like the history of interview questions, or you can do certain tasks in an hour instead of a day, uh, or some new features with TLA Plus, his main thing. Uh, Subscribed to a handful of others. So Jeremy something who writes about the applications of math and programming. There's Eric Norman, which I know his is popular. I'm not subscribed to it, but I just know that I just basically know because one of his articles was summarizing one of my articles. So there are a bunch of people.
Oh, I think I lost connection for a little bit.
Hmm.
Very well. In any case, you're gonna say anything else, or you were finished?
No, that's had a great time today. Thanks for having me on, and listeners, I hope we got the opportunity to talk with you. And
Yeah, it was a really nice conversation. Thank you so much for being in the show. I'm sure everyone has enjoyed it as much as I did. And don't forget, people who are listening, that everything that we talked here is going to be in the links in the description of this show. So see you guys next time. Bye bye.
goodbye.
Well, that was it for today's conversation. I hope you guys enjoyed it and learned as much as I did. It was a really nice conversation. Jimmy is super smart and very knowledgeable in his field. If you want to hire his services, you know where to find him. All those links will be in the description. Now, you guys probably noticed that the quality of my sound wasn't that great. When I finally have a guest who has a really good mic, my mic is not great, and that's because I just lost the cable of my microphone and I couldn't get it. I've been moving around in Brazil and things are just really chaotic in my life right now. So I really apologize for this. I hope it will not happen again, but I can't really promise. But things still went very well. His microphone was great, and I was just there to ask those questions. So things were all right. Well, with that out of the way, if this is your first time listening to this podcast and you liked it, send it to a friend. It will help us a lot. Send us an email at typetheoryforall@gmail.com. Like us on Twitter at @TT4all. Leave us a comment in our website, typetheoryforall.com. We are always so happy when we have comments. It means people are listening and are enjoying things, right? Most importantly, don't forget to pay me a coffee at Ko-Fi-typetheoryforall. I really like coffee, so I would really appreciate that. It's just a coffee. Come on, you're not that poor. Show some support to one of the few Type Theory podcasts still alive. Come on, you can do this. Now, if this is not your first time and you haven't supported yet, come on, shame on you. And did you guys see that I've been posting a lot of memes on Twitter now? I've been spending some time to think about memes. I'm having a great time. They're so funny to do. Make sure to go there, look at those memes and send to your friends. If you have some memes idea, also send to me. I will be very happy to make a meme out of your idea, or just send the meme out straight and I'll retweet or anything. Let's just fill the internet and Twitter with something joyful and not those hateful comments that you see on Twitter all the time, right? Anyways, I think that's what I have for you guys today. So I'll see you next time.